Okay. I also brought some problems that other people would ask me that I thought were pretty good. There's a new chocolate. I'm gonna clean these doors and then lock the door. So, this was one problem that someone asked me. I think it's from Web Design, and I think this is a pretty good problem because what tends to happen here is students see this and they're like, oh good, I'm going to panic. I have no idea what to do. Here's a cubic, here's an inequality, I've never seen these two things together. What should I do? Factor. Now this doesn't factor in any sort of like really obvious way, but I know how to factor. I've got a bunch of tools, right? So I've got the first tool that should come to mind is the rational roots theorem. Because in general, we're going to give you ones that factor over their rational roots. So they're going to have at least one such factor. Once we split that factor off, the other ones come for free, right? Because of the quadratic formula. So we just need to pull one factor out of this. And if you get something like this on the exam, it'll have a rational root. Or maybe they'll even give you the root. They'll say like, blah is the root of this, and now you should know what to do with it. But if they just give you this problem as that is, then rational roots theorem. And the rational roots theorem tells me what? Yeah, if there is a root, a rational root, then it is in this set, right? And this set is, I'm going to start from the big numbers and go down plus or minus 52, plus or minus 26. Where are these numbers coming from? Factors of the last one over factors of the first one. So factors of the constant over factors of the leading term. So this one has a couple factors, right? It's got like 52, 26, 13, 4, 2. This one has two factors, 1 and 2. So plus or minus 13, plus or minus 4, plus or minus 2, plus or minus 1, plus or minus 1/2. Oh, and I missed the factor. I guess it would be plus or minus 4 there. Plus or minus 13 halves. I didn't need 26 over 2 or 52 over 2 because that's 13 and 26 respectively, right? Plus or minus 4, plus or minus 2, plus or minus 1, plus or minus 1/2. So that's a bunch of factors, right? Like that's a whole bunch. And that's going to be like kind of painful if I want to do it. Because I've got whatever that is, 18 factors, right? So, and do I want to like try and guess and check? I mean, that's an idea, I suppose. It's not a very good one. But we have some other theorems. And this is like the importance of these theorems. Like the theorems are the tools that you use to solve particular problems. They're big general tools. And we have this theorem called the intermediate value theorem. Now this is a cube, right? And like, because it's a cube, I know for sure it has a real root, right? It's not hopeless. Like this could be moderately hopeless if it was something with an odd order. The odd order definitely has a real zero, right? And trying to factor something that doesn't have a real zero could really produce some problems. So there's a real zero somewhere. And the intermediate value theorem says that if my function, let's call our function f of x, is continuous, right? And this is continuous, it's polynomial. Polynomials are continuous. If it's continuous and f has some value at one point and another value at another point, it takes on all values in between. So that's a stronger statement than we need. In particular, all we're looking for is we're looking for a place where f is negative and another place where it's positive. Because it's going to have a 0 in there. And if we pick a smart selection, we know where to start working, right? Like we can narrow this selection down so that I'm not trying 18 things at random. So what I would do would be, I'm going to pick something that's not a 0 of this, but I'm going to pick something that's easy to compute, f of 0. Like I know for sure that's not a 0 because it's not in that list of rational roots. But it is negative, right? It's negative 52. So I don't really care that it's negative 52, I just care that it's negative. Now I'm going to pick, I don't know, this is positive, this is positive, this will be negative, this will be negative. You know what? I could pick 13 right here. Because 13 cubed is a big number. It's 1,000, it's more than 1,000 already. It's going to get close to 2,000 and it's times 2. And so all of this is going to be positive for sure, right? So f of 13 is positive. So now I know for sure by the intermediate value theorem there is a root between 0 and 13. So look at how many fewer things I need to check now, right? I'm only looking from +1/2 to +4. Now, granted, this doesn't say there's not roots outside of that. It's totally fine. It just says there is a root in there, right? So there is a root in 0. Everyone understands how I got this far? So this is the sort of reasoning that you should write down. All right, so now the third thing I should do is pick my method of factoring. I personally would go with synthetic division because synthetic division will also help us in another way. Because synthetic division evaluates f at a particular number, right? It evaluates my polynomial function. And as a result, like I can cut this interval in half again if I pick smart, if I pick a good number, even if it's not the right number. And if I'm lucky, it'll be the right number, right? This says between 0 and 13. So let's pick synthetic division, and let's pick, so what numbers are left? From +1/2 to 4, right? I can pick either +2 or +4. What do y'all like? 2. Okay, y'all like 2? We'll go with 2. Maybe we'll get lucky. So now to carry out synthetic division, I write this out. And I take 2. Notice I said 2 or 4, right? Because if it doesn't work, if one of them doesn't work, it tells me the zeros in the other half, right? Or in that half. Do you see why? Because when I'm done with synthetic division, either I'll have a positive number or a negative number if I don't have 0. And if I have a negative number, then I know it's in that half from like 4 to 13, right? Because it went from negative to positive in the interval from 4 to 13. So that eliminated half of the things I need to try again. So I can really whittle down what I need to do and solve this problem intelligently. Instead of like, otherwise you could be guessing and checking all day and you could make even a numerical error somewhere. This sort of like eliminates the possibility that you make a numerical error because you know that this is a problem that's being given to a pre-calculus class. So probably this factors over rationals. 1. So 2, we know there's a 0 in here. So now we just need to start looking. Okay, 2 comes down. 2 times 2, 4, 17, 34, 26. Looks like we got lucky, right? 52. 0, right?
What happened if you would have gotten a remainder?
If I got a remainder, like if I did this with 4, I get a big positive number here. I get a big positive number at the end if I had done this with 4. So that tells me that between 0 and 4, there is a 0. So then I can forget about the numbers between 4 and 13. That's what I'm saying you can do. You can keep cutting that in half with the intermediate value theorem, instead of doing it totally naively and having... Now, there is a possibility, too, that the 0 is irrational. You could always like pick an interval, and that interval now contains an irrational 0, and you're not going to arrive at it by synthetic division. So that is a possibility. But you'll get there very fast. You'll get to the point where you know you're at, because each time you're dividing the set in half. So, and that means you're only going to be able to do that about 4 times at most. All right, so now we know that that f of x is x minus 2 times and then you can either factor or use the quadratic, whatever this turns out, it's nice. This factors as oh, maybe it's plus, yeah. Is that right? So, right, 2, 4, 13. Yeah. And that's how this factors, right? So we've got some choices here too. Like, she's got this method where you do stuff like this. On the number line, 13 over 2 is like 6.5. So those are all your zeros, right? And all she's looking at is whether it's positive or negative on each side, right? Now, we can actually do this with our knowledge of graphing polynomials, right? Because you know how to graph a polynomial. Did I make a mistake? It's possible.
For the 2x, it would be like negative 13 over 2, right?
Why would this be negative? 13 times 2, unless I made a mistake.
Oh, no, I mean like when you put the dots on the graph, the points on the graph.
Oh, yeah, you're right. I'm sorry. Yeah, thank you. Yeah, it should have been negative 2 and negative 13 over 2. You are correct. Thank you. So it should have been right here, not there. Yes. Good call. My fault. Still, this is a cubic equation, right? And honestly, you know enough about cubic equations that once you have a factor, you can graph it pretty easily, right? Because you know it looks like this at the ends, right? You know it looks like this. And now you know your solution sets, right? So, because this is saying where is that graph greater than or equal to 0? And it's greater than or equal to 0 from negative 13 over 2 to negative 2, union 2 to infinity, right?
So whenever you see the, like what is that called? Like, more than or equal to, that's when you know that the parentheses, like of the actual problem, right?
Right here?
Yeah.
Okay, I had brackets here.
Yeah.
Because it's equal to. And if it had no equality, if it was inequality, then, oh, this shouldn't be a factor, this should be a, yeah, sorry. Let's see how many errors I can make before we're done. But, my secret test of you, what happened to this chalkboard? Like, that was not even there like a few weeks ago. Okay, I just can't imagine what sounds. I was like, dang, show you who's boss. Now, you could have also done it with just a number line, and this is how Cornwall likes to do it. And she goes like this, -13/2, -2, +2, and then she plugs in a number over here, like, you know, pick some number, like -100. That's the left of that. Oh, it's clearly negative. Pick some number over here to the right of 2, 100, clearly positive. So that's just using the end behavior. I can just neglect all the terms except for the first one and the last one. Or except for this one, right? Like when I put in a big enough number, these terms don't matter. That's big enough negative or big enough positive. Now here, I need to be a little cagier. If you want to pick numbers that don't work out super bad, like 3 is a good one. That's to the right of -2. That would be 1. This would be positive. This would be positive. So it's positive. You see, I didn't even bother evaluating. I just know that positive number plus positive number is positive. Positive number plus positive number is positive. And then to the left of this, how about -3? Well, then this is -5, right? And this is -1. So those two multiplied give me a positive, and this one's positive. So, oh, I've got a mistake somewhere. This one should be negative, shouldn't it? Negative, I put in, oh sorry, I should have put in 1. Did I say, I said 3. I meant to say 1. I put in 1 here, I get a negative, positive, positive, so that's negative. So, I'm more inclined to do it this way because to me, like, I see the graph when I'm confronted with the algebra. I'm more visual, but you can do it either way, sort of algorithmically or that. And all I'm doing is I'm picking some number here. So I picked 1 here, I picked -3 here. On the ends, it's a little easier because you can pick really big numbers and then you don't care about anything except for the first term. The term with biggest degree.
And you always go, if you're doing that, you always go back to your factor form, right?
Yes.
The last factor.
Yeah, the factor form is much faster than trying to plug them into, yeah. Because here you actually have to do do each of the operations, especially if you have lots of sign changes. Here, you just need to see whether each factor is positive or negative. Because if you get an even number of negative factors, it's positive. And if you get an odd number, it's negative. And that's all you're looking for. So this could be like 10 things long, and it's still really easy to evaluate because you put in like some number, like 10, let's say, and you look, is it positive, is it positive, is it positive, and you just go through them like that. Does that make sense? There's room here if you want to move this. So I don't think you said way over there, unless you just really like that chair. And then another one that I was asked about, there's a rectangular parking lot. Rectangular parking lot. With perimeter 440 feet. We want the area to be at least 8,000 square feet. What are the possible values of length? It turns out it doesn't matter because it's a rectangle. We could have said length or width, and they're going to come out to be the same. So you don't have to worry too much about that. Usually it's problems with sort of structure like that. All right, I got a bunch of words. Probably I should turn them into math, and probably in sort of a clever way. But a good thing to do is to draw a picture. a beautiful rectangle. All right, so I have this beautiful rectangle. What's a good thing to do at this point?
X and Y is your.
Sure, x and y. We'll make x the, do you want x to be the width or the length? Width, okay. And y is the length.
And which ones do they want both?
They're asking for the length, yeah. So just y is what we're going to end up solving for. So that'll help us make some decisions. Now we know some stuff. Let's write some equations. Like we know the perimeter is what?
2x.
Perimeter is 2x plus 2y. Moreover, I have a value for this, which is 440. Right? Now we know I put the little box because it's a rectangle. Perimeter of the rectangle. And the area of the rectangle is x times y. And we know that that needs to be, what does at least mean? Yes. Now, what we can do is we can use one of these equations to substitute into the other equation. I suggest, since this is an inequality, we're much better off using the equality to substitute into the inequality. And we're solving for y at the end of the day, so let's solve this for y. So this right here, I can divide everything by 2, make it a little simpler, right? And now I'm going to substitute 4x, so that's going to be 220 minus y. And now subbing this, subbing 1 into 2, we have 220 minus y times y is greater than or equal to 8,000. We're getting close. What do we need to do? This is what kind of equation? Quadratic. Distribute, and how do we solve quadratics? Yeah, you could complete the square. I would suggest just moving this over first, right? You could do that. You could complete the square first. I mean, I would usually, at this point, just do the quadratic formula. So, I think this even works out not terribly in the quadratic formula. I mean, it's a little, the numbers are a little bit cumbersome for sure, but it's like negative 220 plus or minus 220 squared minus 4 times negative 1 times negative 8,000. So that's going to end up being a minus all of that over negative 2. All right, let's do some computations. Negative 220 over negative 2 is 110 plus or minus 220 squared. Let's do that off to the side. 220 squared. It takes a little bit of work, but it's not. Okay, there's 0. 0, 2, 4. Right? So this is 48, 400. Is that what everyone got? And it's going to be a minus, and it's 4 times 8,000. Yeah, so that one's not too bad. And then all this is still over minus 2. This is positive 16,400. All that over minus 2. All right, so now over on the side, 16,400. 4 definitely goes into that, but I'm just going to do it like this. 2, 8,200, 2, 4,100, 2, 20, 50, 2, 1025, 5, let's see, what's that? 205, 5, 41. And that's what it is. 41 is prime. So that means every time I see 2 of these factors, I can take them out of the square root. All I did was write a factor tree. I just divided by 2, by 2, by 2, by 2, ran up 2, started dividing by 5s, because it ends in a 5. And then 41 prime, you could try to divide it by stuff, it doesn't. So, so every time I see 2 2s, I can take a 2 out. Another 2, so that's 2, times 2 is 4, times 5 is 20. So I've got 20 root 41, plus or minus 20 root 41 over -2. That simplifies to 10. Minus plus, so it doesn't really matter. The negative flips the plus minus, but it doesn't really matter. So, because you're going to subtract it on one end and add it on the other. So now, the last thing I have to do is say, and you might don't have a calculator, but I want to know, for instance, like y is a length, and so it has to be greater than 0, right? 0 is not a length. And so is 110. Also, let's look at what we know about parabolas before we start answering this, because this is an upside down parabola, right? This is an upside down parabola. And it's got zeros, so we know it looks something like this. The only problem we can run into is these are the 2 zeros we just solved for. One of them could be to the left of 0, right? That could be a problem. Like, this is one possibility, this is the other possibility. See, do you all understand how I knew that it had stuff above the x-axis, right? Because it's opening downwards and it's got zeros. If it was opening downwards and it had no zeros, then it had to be all completely below. Yes?
So if the inequality is always asking about the y value,
Yeah.
it's greater equal to
Yeah, I mean, in general, most mathematics is asking you about the y value. So you're just, because usually the y value is the thing you're interested in. Like here, the y value is the length. So, and we're just trying to figure out the constraints such that, by y value, you meant value in the range. Because I picked the term y here, yes. So not the y value, yes. But the range, yes. So we want to see whether it's this case or this case, because if it was this case, then we would have to cut it off. So really, 110 plus a positive number going to be positive. So this one over here is 110 plus 10 root 41. I don't care what that number is. That is an answer, and that's good enough in an unsimplified form. Now, what about minus 10 root 41? Well, I have to say, what is root 41 about? What's a root that's really near 41 that you know?
49.
Yeah. So 40, and root 49 is 7. And in fact, it's definitely bigger than root 41. So this 110 minus 10 times 7, 110 minus 70 is still positive. So it means over here, we have 110 minus 10 root 41. So you all understand why I had to make that consideration. Because it could have been over here, in which case I just chop it off at 0. So if it had been to the left of 0. Like if it had been, say, 10, I don't know, root 200 or something, then that would make it big enough that it would make it negative to the left. 41. So that's what it looks like. And now my solution then is just this. Y is between 110 minus 10 root 41, or I can even just say y is in this interval. 110. Yeah. Minus root 10 root 41. 110 plus 10 root 41. Let me erase the other stuff so it's less confusing to look at. So it's not really germane to the solution of the problem. All right?
So if it was negative, it would just be 0.
Yeah, I would just replace that with a 0. So, and I would actually replace this with parentheses because I can't have my length be 0. Now, what would happen, here's a question for you. What if I'd done all this and gotten there were imaginary solutions for this? What would that have been in terms of the original problem? It's just a good conceptual question. So I got to right here, I wrote down everything nicely, I do this, and then I see the discriminant is going to be negative. What does that mean? And what does that mean? If it only had imaginary solutions, what did that mean? In terms of my original problem. It means that I can't satisfy this problem. Like, I could really easily make that, make it work out like that. If I put if I put, let's say the area is greater than 1,000,000, I guarantee that there's only imaginary solutions because I simply, with this perimeter of parking lot, I can't get an area of 1,000,000. There's a finite range of values that it can take on. So the constraints are just unsatisfiable. And this sort of thing shows you, like, this is a nice application because it's like a super simplified sort of real world thing that, like, you know, let's say you're an architect and you want to build a building and you want the building to be moderately useful. You sort of understand why buildings in general have the sorts of shapes that they do have, like they're roughly rectangular. So you get all sorts of nice things out of this. All right. Now, what problems do y'all have? You have particular ones from the... So those were two that people asked me that I thought were particularly good, because I think it's very likely you get something like this-ish on the test. So, the other thing I do want to talk about, too, is I want to spend a second at the end, I'll come back and talk about transformations.
One thing that I always get wrong is negative x minus 1. And she always expects us to kind of like take out our negative and then it's x plus 1.
Yeah, and that's the proper way to do it.
Yeah.
You want to factor first, but you still do the left or right shift, the horizontal shift still comes first. So we'll do that for sure, and I'll do that with a couple of examples of both logs and exponential.